lesson 8.5, we'll be looking at this idea of logarithmic functions. And first we're going to actually start off with some exponential function, and the reason we do this is because they're going to be related. So what must be the value of x in each equation? Well, 2 to what power gives me 8? Well, we know that in this case x would have to equal 3, because 2 cubed is equal to 8. Another way we could think of this is 8 is 2 cubed. And one important fact here is when you have a power, if the bases are the same, then the exponents have to be the same. So I wrote it here so the bases were the same. They were both 2, so therefore the exponents have to be the same or equal to each other. So 7 to what power gives me 49? Well, in this case, x would have to equal 2, because 7 squared is 49. This one's a little more difficult, and we can use the idea I mentioned up here. If we can write the powers with the same base, then we can say their exponents are equal. Well, I know that 9 is 3 squared. So right now I have 1 over 3 squared, but we learned when dealing with the rules of exponents that if we have power in the denominator, we can move that to the numerator and make this an exponent a -2. And so now we have 3 to the x equals 3 to the -2, so x has to equal -2. And we get to this last one, 4 to the x power equals 18. Well, we can't write 18 as 4 to a power. In fact, we know 4 squared is 16 and 4 cubed is 64. So this one we don't know, and we actually, as of right now, don't have a way to figure this out. And that's why we have this idea of logarithms. So logarithmic functions are inverses of exponential functions. If we go back here, we can't solve something like this. Now, in algebra, we learned that we can solve something like 2x equals 12. This is 2 times x equals 12, so we can use the inverse operation of division to solve that. Or we have 3 plus x equals 7. We could subtract 3 because the inverse of addition is subtraction. Well, we needed an inverse of exponents, and logarithmic functions are inverses of exponential functions. So here's the definition of a logarithmic function, assuming b and x are both positive numbers and b does not equal 0. So we're more familiar with this. So b and x both have to be positive, and b is not equal to 1. If it was equal to 1, we would just have 1 to the y power, which is always 1. So it wouldn't be a logarithmic function. It would just be a linear function. So, and then we have this statement. This is making a statement that compares exponentials and logarithmic functions. Y equals log base b of x if and only if x equals b to the y. So we notice a couple things here. The base of the logarithm is the same as the base of the power here. And then we're also going to mention this later, but the logarithm is equal to an exponent. So this y here is going to be the exponent. And so we're going to do some work in switching between forms. So here's what I mentioned. The logarithm of a number is the exponent. So the logarithm is equal to an exponent when the number is expressed as a power of b. And so here we see a logarithm being expressed as an exponential. Actually, the way that I normally do it, which helps me for some reason, is I say the base of the logarithm is the same as the base of this exponential here. So I would say 2 to the third is equal to 8. And I know that doesn't seem like much difference, but I'd like to think of the base first to this power. So over here, we could say 3 to the -2 equals 1/9, or as is written here, 1/9 equals 3 to the -2. And so here are the two forms of the same thing. X equals b to the y is the same thing as saying y equals log base b of x. So the exponent is what's equal to the logarithm. So we're going to get a little bit of practice here converting from logarithmic form to exponential form. And so I like to say, well, here's my base. So the base, sorry, I messed that up already, base to the third power, because the logarithm is equal to the exponent, equals 125. And these first ones are nice because we are familiar with this. 5 cubed does equal 125. We're a little more familiar with exponentials than we are with logarithms. So this one here, we can say 3. So 3, the base to the first power. So 3 to the first equals 3. And for this last one, we can say 10 base to the exponent, -2, equals 1/100th. And so we converted from logarithmic form to exponential form. It's going to be a very important skill that you need to have. And then vice versa, we're going to convert from exponential to logarithmic. So as mentioned before, we can have log, the base of the exponent is the same as the base of the logarithm. So log base 2 of 16 is equal to, and remember the logarithm is equal to the exponent. This next one, log base 10, base of the exponent is the same as the base of the logarithm, of 1 is equal to the exponent, 0. This is an important one because log base any number of 1 equals 0, because any number to the 0 power equals 1. And then this last one here, log base 2 of 1/8 is equal to the exponent of -3. So in those first two examples here, we showed how to convert from exponential to logarithmic and from logarithmic to exponential. These next few examples have evaluate, and we want to find the value of what is this logarithm actually equal to. Now, hopefully we'll get better and better at this as we use logarithms, but what we actually do here is we think of this as equal to some variable. Let's say it's equal to y, and now let's change this to exponential form. So we have 3 to the y power is equal to 1/81. And we used this idea before. Well, 81, it would be nice to have this as written as a base of 3. 81 is 9 squared, but we know 9 is actually 3 squared. And so something helpful to know is that 81 is actually 3 to the 4th power. So we can say 3 to the y equals 1/3 to the 4th. And then we have this rule for exponents. If we have 3 to a power and a base, we can bring that to the numerator. Sorry, in the denominator we can bring it to the numerator and make this a negative. And now that we have the same base, we know the exponents have to be equal. So y equals -4, which means this we just wanted to evaluate, so this logarithm, log base 3 of 1/81 is equal to -4. And so we evaluated that. We found that it was -4. A few more examples along the same lines. Let's say this is equal to a. We can say 2 to the a power equals 8. We encountered this earlier. 8 we can think of as 2 cubed. And now that we have them as the same base, we know that the exponents have to be equal. Also, once we got to this step, 2 to the a equals 8, we should know that 2 cubed equals 8. Let's say this is equal to b. So 5 to the b is 25, and we're now thinking, well, 5 to what power is 25? We know b equals 2. We're doing more and more of these, so we should be able to think about these and realize what they are, sometimes without writing them as exponential. 5 to what power gives me 25? A couple more that have a little bit of a twist to them, so we can say, well, let's say this is equal to x. 2 to the x equals 1/4. And we would like to have the same base. Well, 1/4, we can write this as 1/2 squared. And again, as mentioned before, since we have a power in the denominator, we can bring that to the numerator and write this as a -2. So therefore x equals -2, which means this is equal to -2. Nine to the a equals 3. There's a couple different ways to think through this. Let's kind of use our same tactic as we have on the last ones. We would like to have these to be the same base. Well, in this case, this is actually the larger number, so we're going to write this as 3 squared to the a. And we know when we have a power to a power, we multiply, so this is 3 to the 2a equals 3, and we know that this is a 3 to the 1. And so when the bases are the same, the exponents have to be equal. Dividing by 2, we get a is equal to 1/2. So this is equal to 1/2, which I just want to show you something here, which we could have realized here. If we wrote this as 9 to the 1/2 equals 3, so changing this, we're putting the one, changing this, then let's get rid of the a. Changing this to exponential form, we would say 9 to the 1/2 equals 3. My writing is getting bad here. What does to the 1/2 power mean? Well, we learned earlier that to the 1/2 power means the square root, and so this does make sense that the square root of 9 equals 3. So being familiar with your rational exponents is going to be helpful. We now want to take a look at a few special cases. Log base b of b. So if your base here is equal to this number here and it has an exponent, it's just going to equal that exponent. The reason why this is true is if we changed this back to exponential form, we could say the base to the exponent is equal to our number here. Well, it's obvious that b to the x does equal b to the x. So this is a identity, really a fact that's always true. And over here, same idea. If you have something to a power of a logarithm with the same base, it's just going to be equal to this number out here. Again, the way that we show this is true is we're going to change this to logarithmic form. So we have, this is an exponential here, b to this power equals x. Well, let's change that. We have log base b, so this b here, of x is equal to our exponent, which they are the exact same thing. So we have a couple identities there that have to do with logarithms and exponentials. Another concept that we want to mention is this idea, I know it's down here, of common logarithms. Our decimal system, our system of numbers, is a base 10 system. And so this base 10 is important. That means we have 10 digits, 0 through 9. And if we have a log base 10, we actually don't need to write that 10. We can just write it as log of x. So it's an understood 10. So I would compare it to when we have something like this. There's no number written here, but we know it's a square root. It's an understood square root if nothing's written there. So if there's a log of 7 or something like that, it's an understood base 10. And that's called a common logarithm. The last thing we want to do is look at the graphs of logarithmic functions. We've already looked at the graphs of exponential functions, so here's y equals b to the x here in red. We knew that it went through the point 0, 1. The domain is all real numbers. The range is y is greater than 0. And we also see that there is a horizontal asymptote here at the x-axis, or y equals 0, and we notice it's the negative part of the x-axis. Well, since we're talking about inverses, exponential functions and logarithmic functions are inverses, the domain and range will be switched. So the domain here was all real numbers, which means the range will be all real numbers. The range was y is greater than 0, so our domain is x is going to be greater than 0. We have our dotted y equals x line here, and we know that inverses are reflections over the y equals x line. So if we take our exponential function here, flip it over that line, we'll get our logarithmic function. So our logarithmic function has a couple properties that are always true about the parent function, at least, and here they are. Here's the still the blue is the graph of y equals log base b of x. Its x-intercept is 1, 0. It will always go through this point 1, 0. Its vertical asymptote is x equals 0, or the y-axis, and it contains the point b1, so b is our base here of the logarithm. So if it was a 2, this would be 2, 1, or if it was 3, it would go through 3, 1. And then another point that it goes through is the reciprocal of b, negative 1. And so we're going to use those 3 points oftentimes to help us graph a parent function of logarithms. And then we'll do an example where we actually graph some logarithms, and we'll talk through how to do that. We also use this fact that we're going to have a vertical asymptote at x equals 0, which is the y-axis. So we might have a parent function right here of y equals log base b of x. We can use this to help us graph something in this form. And this is very familiar because we've done this with parabolas, we've done this with radical functions, we've done it with exponential functions already, so same idea. A is going to change its steepness. Could also flip it. What's inside here, added or subtracted from x before we take the logarithm, moves it left or right, and this k out here moves the function up or down. So let's take a look at an example here. It says graph y equals 3 log base 2 of x plus 4 as a transformation of y equals log base 2 of x. So we're going to start with this function and then use that to graph this function. Now right off the bat we can say, well, it's going to be steeper and it's going to be moved to the left 4, but first we're going to graph this. We do this because depending on the base, your logarithms are going to look a little different. So as mentioned before, graph this one in black, and we're going to think of a couple values here. We were told earlier, we mentioned earlier that this will always go through the point 1, 0. It will go through the point b, 1, so b in this case is 2, so 2, 1, and it will go through the point reciprocal of b, so the reciprocal of 2 is 1/2, negative 1. And so we can sketch those 3 points on here. So it goes through the point 1, 0. It goes through the point 2, 1. It goes to the point 1/2, negative 1. So 1/2, negative 1. Having some trouble here. And so that's the 3 points, and we know this is a logarithmic function, and we will get more familiar with this, but this is going to come up, go through these 3 points, should be a smooth curve, keeps coming out this way. Should be asymptotic down here, so I did goof up a little bit here, so it should get closer and closer to the y-axis. Now we're going to use that to help us graph this. And I'm going to do it in 2 steps here. So this next step we'll do in red, and then maybe the final answer we'll do in blue. Now we're going to take and use this 3. Now this 3 we know makes it steeper, but what we can do is we can take our points here, take the y values, and we can multiply each of those y values by 3. So instead of having the point 1, 0, we're going to have the point 1, 0 times 3, which is actually still 1, 0. Now we're going to take 2, 1, and we multiply this 1 by 3. So we only multiply the y value because it's 3 times log base 2 of x. So 1 times 3 is 3. And then for 1/2, we're going to multiply negative 1 times 3, and that gives us negative 3. So we have these 3 new points. So we still have 1, 0. We have the point 2, 3. So 2, instead of 2, 1, we have 1, 2, 3. And then we have the point 1/2, negative 3. So here's 1/2, negative 1, negative 2, negative 3. So there's that point. And we're going to try to sketch our graph through here. Having trouble getting this right as I'm drawing it. And so there's that graph. And now lastly we can take this graph and move it left 4. And now what we want to do is move each of these points to the left 4. So I'm going to take this, move it left 4. So 1, 2, 3, 4. That one will go here. We'll take this point and move it left 4. Sorry, not that one. We're dealing with our red one. 1, 2, 3, 4. And we'll take this point and move it left 4. So 1, 2, 3, and 4. And then we'll sketch our logarithmic function there. So we come up through here and comes out like this. Something to realize here. So it used to be that the y-axis, or x equals 0, was our vertical asymptote. Well, now it's x equals negative 4 is our negative asymptote. So that's how you can graph functions. The tricky part is sometimes this 3. So what we did is we took our parent function, multiplied each y value times 3 to find 3 more points, and then you can shift left or right. We also, if there was like a plus 3 out here, we could have taken each of these points and moved them up or down. And that is the introduction to logarithms and logarithmic functions.